Corona video number 12, dealing with the bending of light and Snell's law at BHS, the Harvard of the NVL. So what we're going to do is we are going to first talk a little bit about something called the N value. So as we try to understand how light's going to move through different objects, the first thing we need to discuss is N. What is N? N stands for something called the refractive index. And what it is it's comparison. So N is going to be equal to the speed of light in air or vacuum, C, which is always the same number, it's a constant. So I'll say speed of light. Now there is a difference between the speed of light in air and a speed of light in a vacuum, but it's basically the same thing. It's not much different at all. So we're just going to say air, and we're going to divide it by the speed of light, of a particular media. It could be lots of different things. Here's some things that would have N values, things that light can get through. Well, light can also get through water. And so we find the N value of water, if you look it up, to be 1.33. Also glass. There are different kinds of glasses which have slightly different N values. But for now, we'll just say glass. And even something like diamond. Diamond has a really high N value of like 2.5. So we'll use those three things as our examples here when we're trying to understand why light bends. So to kind of answer why light's going to bend when it goes through one media to another, the answer is because it's going to speed up or slow down. So that speeding up and slowing down can be seen as bending. So let's just see how much it speeds up or slows down when it goes into these different objects. So we'll rearrange this to get V. So if we take the speed of light in air and divide it by N, we can figure out the speed as it goes into these different things. So let's do it first for water. So I just told you that the N value for water is 1.33. The speed of light in air or vacuum is going to be 3 times 10 to the 8th meters per second, 670 million miles an hour. And then we can just divide these two things and we can get how fast it's going to be going when we go into the boundary or when it bends. So it's going to slow down because the N value is higher. So when you slow down 3 E8 divided by 1.33, we're going to get 2.25, let's say 2.3 times 10 to the 8th. So what's the speed of light in water? 2.26 times 10 to the 8th. And you can see the slowing down is going to be why light's going to bend. It'd be like if you were driving your car and all of a sudden you went from pavement to gravel. If you were making a turn, all of a sudden you would bend a little bit differently, or you would drive off in a little different direction. It's going to be kind of like that when light hits something. So that's one of the things I wanted to look at, and then we'll do an example of this in just a second of water. Let's look at the other two examples. So I'm just going to set this paper off to the side and come back to it in a minute. So what about V in glass? Like, we already know it's going to be even more of a change because it has a bigger N value. So if I put 1.5 in for N, and I put in the speed of light up here, what's going to be the speed of light in glass? So I'm going to do 3E8, and then I'm going to put in my N value of 1.5, and I'm going to divide And so I get 2 times 10 to the 8th. 2 times 10 to the 8th meters per second is V. So the V in water was 2.26, and then the V in glass is 2 times 10 to the 8th. What about in diamond? Let's do it one more time here. So V in diamond is going to be C over N. We put in 3 times 10 to the 8th up here, and now we divide by 2.5. So once again, 3E8, and we want to divide it by 2.5. We get 1.2 times 10 to the 8th. So it slowed down even more. So you can see each time we did it, we're getting a slightly different speed. So first we did water, 2.26, basically 2.3 times 10 to the 8th. Then we did it for glass, 2 times 10 to the 8th. Then we did it for diamond, 1.2 times 10 to the 8th. Now, we can use that information and see how a beam of light would interact with these boundary changes. So for example here, we can apply something called Snell's law. So Snell's law allows us to make predictions of how much it's going to bend when it approaches a boundary. So Snell's law says n, which is the refractive index, of the incident angle, that's the beam of light as it comes in, times sine of theta, that's the angle it's approaching. So this is the incident refractive indice, and this is the angle as it comes in. So this would be like air and maybe, I don't know, 40 degrees. Afterwards, we go into a new material. We'll call it NR. So this is after it's bent. And then we're going to put sine theta R for the angle after it bends. So in order to have bending occurring, you have to have a boundary. So here's a separation line. And then we're going to say that this will be air. So this would be where it's coming from. Then I'm going to send it through water. And we're going to watch how it bends. Now when you do this, you have to create a perpendicular line that you can measure from, called the normal. So the dotted line here is our normal line. So as I enter at some angle off of the normal, so I'm going to measure off the normal here. I'm going to enter maybe 30 degrees off the normal. So my beam of light is going to come in like this. So this is going to be theta I, and I told you that it was 30 degrees. And we know n of light is 1. So 1 times the sine of 30 is going to be equal to nr, how much it's going to bend that angle. So we said water was 1.33, and we want to solve for how much it's going to bend. Then we can draw it. All right, so you want to make sure you're in degree mode before you do any of this stuff, because if you're in radians, you won't get the right answer. So the sine of 30 is 0.5. So we get 0.5 equals 1.33 times the sine of theta r. So then we're going to divide both sides by 1.33. So 0.5 divided by 1.33 gives me 0.38. So 0.38 equals sine theta r. So then I'm going to just divide, or inverse sine. So take your answer you just had and press second sine, and then put that answer in there, and you're going to get the angle. So if it comes in at 22 degrees, If it comes in at 30 degrees, it's going to leave at 22. So I'll use my protractor and I'll measure off the dotted line and I'll do 22. And so here's the angle that we leave. We approached at 30, we leave at 22. Now the reason that it bends toward the normal is because it's going to slow down. And you can tell it's not a straight line. Look, I'll line up my protractor. See how it's bending? How much did it bend? Well, it bent about 8 degrees as it went towards. So we came in at 30 from the normal, and we leave at 22 based on the normal. And the reason that we're bending is because we're slowing down. And this is what Snell's law is all about, the bending, allowing us to make predictions. Now we did it for other things too, right? We didn't just do it for water. We also did it for glass. So let's check that out. Let's look at what it's going to be like for glass here. Trying to find a piece of graph paper. There we go. So when we do it for glass, we'll do a similar kind of setup. So we're going to have this boundary that's occurring, and then we're going to have a perpendicular line being made here, and we'll call this air, and then we'll go into glass this time. Remember, the end value for air is 1, and the end value for glass is 1.5. So we'll come at a similar angle, just to kind of keep things consistent, to make comparisons. Let's come in with 30 degrees again. You can come in any angle you want, right? We're going to come in at 30 to the origin. This will be theta I, and like I said, it's 30 degrees. And then afterwards, we're going to bend a certain amount. Well, how much are we going to bend? Well, it's based on Snell's law. So sine theta I equals sine theta R. So the n values also come into play. So we put in our numbers, 1 times the sine of 30. We just did that last time. It's going to be very similar. And we're going to get 1.5 times the sine of this unknown angle that we're solving for, theta r. So we found out last time that the sine of 30 was 0.5. So we have 0.5, and then we have 1.5. So we divide that by 1.5. That gives us 0.33. We do second sine or inverse sine, and you get 19.47 degrees. So my new angle is 19, we'll just say 19.5 degrees. So if we come in at 30 and we enter glass, we're going to leave an angle based on the normal of about 20, 19.5. You can see that it's slowed down more, and so the bend is more prominent. If we compare it to what we did last time, when we looked at this, we were bending 22 degrees, and now we're bending 19.5. And the reason we're bending more is because we're slowing down even more. Let's do it for diamond, because that's like the extreme. Let's run it for diamond, because that's going to be going really fast. All right, so diamond has a n value of 2.5. So let's create our boundary. Here's my boundary right here. And on this side, we'll have air. Remember, the n value for air is 1. And on this side, we're going to have diamond. And diamond had an n value of 2.5. And then we have this normal line, perpendicular line to the surface, like so. And then we're going to come in Let's do 30. Why not, right? Let's keep the party going. So we're going to come in at 30. 30 degrees. We call this theta I. And then we're going to leave at some unknown angle that we don't know yet. So let's go ahead and we use Snell's law. Ni sine theta I is going to be equal to Nr sine theta R. So we have 1 times the sine of 30. We learned that's the same thing as saying 0.5. And we have 2.5 times the sine of this unknown angle. So what we do is we say sine 30. And sine 30 is 0.5. Then we're going to divide that by 2.5. And then we're going to inverse sine that answer, 11.5 degrees. So if we look at our bending now, we're only going to be bending about 10 degrees. 11.5 degrees puts you about right there. Okay, now you're really starting to see the bending occur. Now you can really start to envision this. So in our first one, it wasn't really all that extreme. At first, we did water. It was only bending 22. Then we did glass. It was bending 19.5. And now we're doing diamond, and we're bending 11. We're bending at an angle of 11.5. Right? We're just bending more and more. Let's make a comparison. Here's my straight line if I continued. And you can see there's a big difference there. Let's talk about the speeds. What was the speed of light in diamond? The speed of light in diamond was 1.2 times 10 to the 8th meters per second. Let's compare that to the other ones. The speed of light of water was 2.26 times 10 to the 8th. And then the speed of light in glass was 2 times 10 to the 8th. So the more we slow down, the greater the bend will be, the closer we're going to bend toward the normal. And this is kind of how Snell's law works. So here, this is a little background for you as you start to get into the FET that we're going to be looking at. All right, so to recap, there are 2 new formulas that we need to be aware of, and those are the refractive indice is a comparison of the speed of light to the velocity in a different media. And Snell's law, Ni sine theta I is going to be equal to Nr sine theta R. Hopefully this makes sense, and you can apply these 2 formulas in our FET. All right, thanks for tuning in. I know 17 or almost 18 minutes is a long time, but hopefully it'll pay dividends for you in the quiz and then also in the FET lab. All right, talk